Welcome to AP Podcast 13.7. This is on Le Chatelier's principle, or as a former instructor from Canada used to tell me, Le Chatelier, or my students sometimes call it Le Chat's principle. But this is a super important concept in equilibrium. I mean, the questions that pop up for this are very common, and you'll see them over and over and over. So we want to make sure that we have this stuff dialed in. So the key to this whole thing right here is that we are looking at a system that is at equilibrium, right? Can't tell you how important that is, but what we're going to do is we're going to say we've got this system at equilibrium, and now we're going to do something to it. We're going to either change the concentration, as you can see right here. We're going to change the pressure, or we're going to change the temperature. And what we want to do is understand exactly what happens to the system when we affect that system by doing those changes. And so there's a few little rules to remember, but it's not too bad, but sometimes it really confuses students. So let's get into this and see what kind of shift it's going to cause to our system. Alright, so here's a couple things. Now, as you guys remember from this chapter, we spent a lot of time with K, but we've also talked about Q, and Q being the situation where the system hasn't reached equilibrium, but we want to figure out what's going to happen to it. Are we going to make more products? Are we going to make more reactants? And so if you really focus on the effect on Q, it'll help you figure out which way the system's going to shift. And here's something to just remember, is the system will always shift away from the added component. Now, I tend to not focus on Q too much. I like to just think about the reaction. So imagine I've got a reaction. I've got some A plus B, and that yields some C plus D, right? And what we're going to do is imagine we're going to add some product to a system. Now let's just say, for the heck of it, for ease of use, that K equals 10, right? So that means the concentration of products over the concentration of reactants equals basically 10 over 1, right? Now imagine that I'm going to add more product, all right? So let's say I'm just going to increase C. I'm going to add it up. Now, we know that this system is at equilibrium when K equals 10. Now, I've just added stuff up here, right? I've added stuff to the numerator. What's going to happen to the system so that it can reestablish itself with a K value of 10? Well, as you know, if I add some up here, we've got to get more of this. This has got to increase. So look at the arrow that I have right here. What that's going to do is that's going to cause the amounts, the concentrations, to shift more that way, because remember, this reaction is looking for an equilibrium of 10. And so let's just make it easy. Let's say all of a sudden I make the value up here 15. All right? Well, I've got to add more of the numerator here to equal 10. I hope this is making sense. And so what's going to happen is you're going to increase your A and B. Now, if you think about Q, if I add more products, that makes Q larger than K, and that's going to shift away towards the Q like we did when we were talking about Q. Now imagine if I'm going to remove some product. So let's say I've got some concentration of D here, and I remove it, I decrease it. All right? Well, I've just decreased this value right here. Remember, at equilibrium, it's got to get to that equilibrium of K, which in this case equals 10. So what's the only way for it to work? The only way for it to reestablish? Well, we've got to make more D. We've got to increase. All right? So if you look at this bullet I have right up here, it's going to shift away from the added equilibrium. Remember, we added some C. Which way did it go? It shifted that way. All right, we made more reactants and decreased the amount of products. But on the other hand, if I remove some product, it's got to shift towards. And so that's a real important thing. So let's look at this in another situation. Let's look at it from the reactant standpoint. All right. Now again, I'll just write out my reaction. I've got some A plus B yields C plus D. And again, we're just going to say that K equals 10. It's an easy number to remember, okay? Now, I'm going to remove some reactant. In other words, I'm going to take A and I'm going to decrease it. Remember, K is established at 10. What's the only way for us to get 10 if I've decreased this number? Well, if I've decreased this number, I've got to have the whole reaction shift this way to make more. And that's what this arrow is up here. Now, again, for those of you that really like the QK thing, think about it. Now, K in this situation, I like to put K over here, Q over there, right? You remember that? K is now bigger. It's going to shift away, all right? Now, if we add reactant, okay, in other words, I'm going to increase. Let's say I'm going to increase some B. Again, I still have to get that value of 10. If I'm going to increase B, in order to reestablish equilibrium, I've got to shift the reactant, shift towards the product side. So that means I've got to make more C and D and decrease a little bit of the A. All right. So hopefully this is making sense. It's really kind of weird, but once you start seeing the problems, you'll see that it's not too bad. Now let's look at the pressure situation. Okay. When you change the pressure in a reaction, the way we do that with gases is we change the volume. Right? So if I decrease the volume, that jacks up the pressure. If I increase the volume, that lowers the pressure. So think about a system that I have right here. I've got all these gases, and what I'm going to do is I'm going to reduce the volume. Now look at this bullet right here. This one's really important. When a volume is reduced, the system will move in the direction that has the least moles. So if you just remember, reduced volume, fewer moles, you're going to be in great shape. All right? And then, of course, on the opposite end, if you increase the volume, you'll increase the number of moles. So let's say I reduce the number, I reduce the volume here. Well, how many moles I have on this side? I've got 1 mole of gas on this side, and I have 2 moles of gas on this side. So if I reduce the volume, all right, and another way of saying that is, of course, increasing the pressure, then the system is going to shift to the smaller number of moles. So it'll shift that way. Now, what would happen if I wanted to increase the volume? And what is that? That decreases the pressure. Now I would want to shift towards the greater number of moles, so I'm going to shift that way. Now, hopefully that makes sense. Now, if we wanted to spend a little time on it, we might do this in class. You could look at this from a standpoint of partial pressure and still getting those pressures to equal that K. But remember, if we're gonna decrease that volume, we're gonna minimize the moles of gas. All right, so here's just a little practice. Let's do A and B. If you want to pause the video, go ahead and do it and try it. But look what's going to happen. In this one, we're going to, what are we going to do to the volume? We're going to increase the volume, right? Increase the volume. So in other words, if we increase the volume, we want to go to a greater number of moles. So let's look at this first one. We've got 1 mole there, we've got 3 moles there, and 2 moles there. So where would the shift go? Well, it would shift towards the greater number of moles of gas, right? What about this one? We've got 1 mole there, 2 moles there. That would cause a shift this way, okay? Now, I want to mention something because this one's tricky. Let's look at this thing right here, okay? Look at this. Solid, solid. So, my question to you is, are those part of the equilibrium expression? Absolutely not, right? So because those aren't part of the equilibrium expression, the K simply just equals this, right? CO2. Okay? So if I'm going to increase the container, where's the greater number of moles of gas? Well, on this side I have 0, right? So it's going to shift that way. All right, hopefully that makes sense. Let's talk about it. One more thing that happens with pressure, and that's what happens when you add an inert gas. All right. Now, if you think about adding an inert gas, and we're talking about that, we're talking about adding some krypton or some argon, something that's not going to react. What happens is that the partial pressures of the reactants and products are not changed. All right. So since we don't change the partial pressures of the gases, and remember when we were calculating Kp back in the day, right? Kp, it was all about the pressure of the products over the pressure of the reactants, right? Okay. Well, if we're adding some inert gas, this ratio is not going to change because is the inert gas going to be part of the products or part of the pressure or of the reactants? It's going to be part of neither, correct? And so because of that, it's not going to affect the equilibrium. So I throw that out there because that's the kind of question that pops up quite a bit. They go, hey, we're going to add some argon gas. What's that going to do to the pressure? All right, next one and the last one. Temperature. Now, hopefully with temperature, you're thinking, wait a minute. K is only for a reaction at a particular temperature, correct? And that is correct, right? So we have to understand, when we think about equilibrium, that change in the temperature is of course going to change the K. But what they want to do is they're going to ask you which way is it going to shift depending on if it's an exothermic reaction or an endothermic reaction. And that's the kind of skill that we want to be able to do, be able to predict which way is it going to change. Obviously, the rates are going to change, right? Because we know there's going to be a new K because we have a different temperature. But that doesn't mean we still can't predict which way the reaction is going to go. And so as you can see right down here, it's going to be completely dependent upon if it's an endothermic or an exothermic reaction. So let's look at an exothermic situation. Now, exothermic reaction, H is given off. As you guys know, it releases heat, right? Now, the easiest way to do these kind of problems is to think of heat as being either a reactant or a product. And then what you can do is you can treat it just like if we added product or added reactants. It makes it very, very simple. So once I've established that this is an exothermic reaction, all right, we know that heat is going to release, I'll just write heat over here. Now, if I raise the temperature, all right, that's like adding heat. So that's heat going up. Which way is it going to shift? It's going to shift away from the added component, right? So that'll cause the reactant to shift that way. That'll increase the amounts here, decrease the amount there, right? If I were to cool this down, all right, if I were to cool this reaction down, that's the same as decreasing the heat, and that would cause the shift to go this way. So as long as we make heat a product or a reactant, these problems become relatively straightforward. So let's look at it from the endothermic standpoint. Okay, so now look where we've put heat. We've taken heat, we've put it right there. We've put it on the reactant side. All right, so if I increase the temperature of this reaction, it's going to cause the shift to go that way, away from the heat. If I decrease the temperature, it's going to cause the reaction to go this way. Right? Hopefully that makes sense. What I'd like you to do right now, pause the video, try number 60, and we will go from there. Okay, so hopefully you can understand what I'm doing here. When we add oxygen gas, that's going to cause a shift right there, so you can see the shift going that way. That's going to cause the SO3 to go up. When we add, when we increase the pressure, that decreases the volume, right? So we're going to be going to the smaller number of moles, and on this side we have 2, on this side we have 3. So that's going to cause the SO3 moles to increase. Adding argon gas. Argon gas is inert, right? Adding argon gas causes the partial pressures not to change at all, and so you're not going to get any kind of change. So the amount of SO3 is going to stay the same. When the temperature is decreased, look where heat is. Heat's over here on the reactant side. Since the temperature is decreased, that's like removing heat. That's going to cause the shift this way, and so it's going to go up. And then if I remove SO2, that's going to cause a shift to the right, and that's going to decrease it. So there you go. We'll play with a lot of the problems like this, and I'll see you next time. Hopefully this made sense.